Hey chemistry, welcome back to another episode of Coronavirus Chemistry. I'm going to keep doing that every single time I make a video. It's pretty funny, I think. Anyway, it's a pretty good day outside. A little cold and gray, but I enjoy the lack of rain. I'm still here in the dining room making videos, so here we go. Now, last time we were together, I made a video about thermochemistry in general, and I was talking about MC delta T, the MCAT equation, which tells us how much heat is transferred when some object is changing temperature. We're going to continue to use that in today's lesson, but we are going to talk about something that is an offshoot of this called enthalpy. Now, enthalpy is this is symbol right here, delta H, and H pretty much stands for heat. Enthalpy is defined as the change in heat during a chemical reaction. So this is, if you take some kind of reaction and you put the reactants together and they go boom, like in a combustion reaction, and the heat is released. So there's a certain amount of heat that is either released or sometimes goes into a chemical reaction. And you should have seen this with the video yesterday, or on Tuesday, the video where we saw the science guy, he put salts into water. Now that is a chemical reaction. The chemical reaction that's taking place is dissolving. The salt, which is a solid, is going into the water and then breaking apart into ions. That chemical reaction either releases heat or takes heat in from the water that the salt is surrounded by. So we can calculate that amount of heat that occurs that either is released or gained by the ions by describing it as called enthalpy. So enthalpy is the amount of heat that is produced in a chemical reaction. It is measured in kilojoules per mole. A lot of you guys have problems with kilo. Remember, 1 kilojoule would be 1,000 joules. So keep that in mind. Its value, either being negative or positive, has a meaning. If it is a negative number, that means that the reaction is exothermic, just like with Q. If delta H is negative, that means the reaction's heat is going out of the system. So in that case, you would feel, if it were in your hands, if the reaction were in your hands, it would feel warm because the molecules doing the reaction would be releasing heat. If enthalpy is a positive number, that means the reaction is endothermic, meaning that the reaction needs heat in order to go forward. So if it's endothermic, heat is going to be going into the reactants, so it's going to feel cold in your hands. Now let's take a look at an example where we're going to use this delta H, this enthalpy term. Let's take a look at this combustion reaction here. Moving off to the side there. We have methane CH4 reacting with oxygen gas right here. And the products of that combustion reaction, of course, are carbon dioxide and water. Now, we are told the enthalpy of the reaction. This is negative 890 kilojoules per mole of reaction. Now, I'm going to put that reaction part underlined because that is actually a really important thing to remember. What this is saying is that if this reaction were to happen 1 mole times, kind of a weird term to use, basically if this reaction were to happen 1 mole times, that's a lot, 6.02 times 10 to the 23rd, something like that, then 890 kilojoules of energy would be released. It's a negative number, so that means this reaction is exothermic, and that means that this amount of energy would release if this reaction were to happen a mole number of times. That's, again, a weird term, but it's important because we're going to relate this to how many moles of each reactant are being used in the process. Let's just jump into an example here. So here's our first example. It says, how much heat is released if 2.5 moles of methane are combusted with excess O2? You thought stoichiometry was over? No way, Jose. We use it all the time. We're still going to use stoichiometry to solve this problem. This enthalpy number is a ratio. It's a ratio of if my reaction were to happen 1 mole times, then this much energy is released. So we can relate the enthalpy value to stoichiometry values. So looking at this one right here, if we had 2.5 moles of methane, well, how many moles of methane are used in one run of this reaction? Well, 1 mole is used in one run of this reaction. It's the molar ratio is 1. For every 1 time this reaction occurs, we use methane 1 time as well. So 1 mole of CH4 to 1 mole of the reaction. If we do the reaction once, we're going to use 1 mole of methane. Okay, so that's the ratio between the mole of reaction and the number of moles of methane, CH4. And then I would then multiply by the molar enthalpy, which is for every 1 mole of reaction, 890 kilojoules of energy are released. So the math is pretty simple, but the setup's a little weird. I think it's sometimes just kind of tricky. But it's going to be 2.5 times 1 times negative 890. Let's go ahead and do that on our calculators here. So 2.5 times negative 890, and we get negative 2225. I'll just go ahead and use 4 sig figs even though I shouldn't. So the answer is negative 2225 kilojoules. So that's how much energy would be released if I used 2.5 moles of CH4. And that kind of makes sense. You're taking 2.5 and you're going to multiply by 890. So that's the process taking place. Now, if the molar ratio wasn't 1-to-1 between the reactant or whatever we're talking about and the enthalpy, then the numbers change a little bit. And you can guess that you're going to use the molar coefficient for maybe water in the next problem. So here's another one. If 100 grams of water are produced, how much heat was generated? Now this is again kind of a stoichiometry problem. We're going to do the same sort of thing. If I have 100 grams of water produced from the chemical reaction, move that over a bit, there we go. So if I made 100 grams, they want to know, well, how much energy was produced alongside with that 100 grams of water? Well, I'll start with my 100 grams of water. I'll convert it to moles by dividing by the molar mass of water. And then I'm going to multiply by the ratio between how much water is produced versus how many times the reaction runs. Again, kind of a weird term, but if I were to run this reaction one time, how much water do I get? I get 2 moles of water. So for every 2 moles of water that are generated, I get 1 mole of the reaction happening. It takes 2 moles of water to get the reaction to happen once. So again, that number 2 is coming from the molar coefficient for the 1 time that this reaction is happening. So 2-to-1, 2 moles of water to 1 mole of the entire reaction. And then the ratio, the enthalpy here, we use that next. 1 mole of reaction. If this reaction happens once, then I make 890 kilojoules of energy. And so that's the stoichiometry there. So 100 grams divided by 18.02 divided by 2 multiplied by 890. Let's go ahead and do that. So 100 divided by 18.02, okay, and then divided by 2, okay, and then multiplied by 890, it's going to be negative. So all rounded to 4 sig figs, we're going to have an answer of a negative 2469, negative 2469 kilojoules. That's our answer. I should have circled that one too. Okay. So if 100 grams of water were produced in the reaction, that's how much energy would be released alongside with those 100 grams. That's the basic rundown of how to do an enthalpy problem in terms of stoichiometry. Let me set up another one, and this is a great time to do something where I'm going to cover this with my calculator. And then I'd like you to pause it right now, and try to work this out on your own. Same kind of process, but do this on your own. I know we're all at home and we're kind of figuring this all out, but it's a good idea to know how to do this problem. And so I'd like you to pause it and try to work out this problem right here. So pause. All right, hopefully you've paused, and we can go ahead and do this problem. So we have a reaction between aluminum and hydrochloric acid, which produces aluminum chloride, and hydrogen gas. This reaction actually should look somewhat familiar. I've used this as an example before. The enthalpy of this reaction is 1049 kilojoules per mole. And the question is, how much heat is generated if 10 grams of aluminum wow, it's bad grammar, are reacted with excess HCl. So same kind of thing as we did with the last problem. So we're going to convert from 10 grams of aluminum to moles, and then we're going to use the molar ratio between aluminum and the molar, the moles of the reaction, which is always 1, and then multiply by the enthalpy. So take our 10 grams, divide by the molar mass. Let's go ahead and do that. 10 divided by 26.98, okay? And then divided by 2, and then times 1049. Okay, very, very similar to what we just did. This is going to be, negative 194 kilojoules. So 194 kilojoules. Okay, very similar to the last problem. So you take the amount of reactant or product that is given, and then you're going to convert to moles, and then do the molar ratio between the reaction and the reactant or product. That number right there always comes from the molar coefficient. So in this case, it's 2. If I was working with HCl, it'd be 6. If I was working with AlCl3, it'd be 2. If I was working with hydrogen, it'd be 3 down here. So this number comes from the molar coefficient with the reactant or product we're talking about, and then we multiply by the enthalpy of reaction at the end there. Okay, now those aren't too bad in my opinion. It's basically just a stoichiometry kind of problem. The next kind of problem, though, that I want to go over is, well, how do we find the enthalpy of a reaction? These numbers just don't come out of thin air. They're made, or they're measured by actually doing reactions. And so let me give you an example of what would happen to figure this out. So remember from the video with the gentleman doing the salt and water. Remember that when he did that, the temperature of the solution changed. It either went up or it went down. That's important. Now, we can figure out how much the temperature changed, and then we can figure out, well, how much energy was actually either taken from the water or added to the reactants. I think that's the same thing. So if the water got warmer, then it would be exothermic. If the water got colder, then it would be endothermic. We can measure that change in temperature, and then we can measure how much heat, how much in energy joules was actually exchanged, and then we can figure out, well, how much energy per mole was actually exchanged. And that would be the molar enthalpy. That would be the enthalpy, the delta H. So we can measure the enthalpy of reaction by measuring the change in the temperature of the surroundings. I want to be really, really clear here. So if we put salt in the water, NaCl into water, it ionizes into Na plus and Cl minus, and at the molecular level, this is what it looks like. I've used a picture like this before. The sodium is surrounded by water molecules. The oxygens are negatively charged, so they're surrounding the positively charged sodium. And then the chloride is negatively charged, so the water surrounded it with positive hydrogen sides of water. And the reaction that takes place is this one. It's NaCl dissolving into Na plus and Cl minus. Now, when it does that, there's some heat exchange. Where does that heat go? Well, the heat is either going to be taken from the water molecules, which are bumping around the chlorides and the sodiums, or the sodiums and chlorines are going to give water or heat to the water. We don't know until we actually do the reaction. So the surroundings in this case for the ionization of NaCl are going to be the water molecules. And that is what we can measure. We can measure the temperature of the water by using a thermometer. So what this is called, specifically when we're dissolving, is we're calling this the heat of dissolution. Sometimes people might call it the heat of solution. This is just this. There's lots of different terms for enthalpy, but in this case, this is the amount of heat that's dissolved, the amount of heat that is generated when a salt is dissolved. It's still going to be the enthalpy, delta H subscript reaction, or just delta H, whatever you want to use. It's still in kilojoules per mole of reaction. But the heat is either going to be going into the ions, or it could be going out of the ions. If the heat is going into the ions, then the waters are losing heat. If the waters are losing heat, then the temperature that we measure is going to go down. If the energy were to go into the waters, if heat's going into those waters, then we would measure an increase in temperature. If we measure an increase in temperature, then that means the reaction is exothermic. If we measure a decrease in temperature, the reaction is going to be endothermic. If we measure an increase in temperature, it's going to feel hot in your hands, so it's exothermic. If we measure a decrease in temperature, then it's going to feel cold in your hands, and that's going to be endothermic. This is really, really important to understand where the heat is going. The heat transfer is a super duper important thing to keep in mind. And a lot of students have a lot of trouble with this every year. I'm just making that very clear. Heat transfers from the ions that are dissolved to water or vice versa. And we can measure that temperature change by using a thermometer. And that gives us whether a reaction is endothermic or exothermic. Let me go ahead and do an example problem where we use something like this and then measure the enthalpy of the reaction. So when 5 grams of calcium chloride, I keep doing this, is R dissolved, 5 grams, that's plural, R dissolved in 50 milliliters of water, the temperature of the water rises from 20 degrees Celsius to 37 degrees Celsius. What is the heat of the solution? I'm going to go ahead and just do this one rather than kind of having it built up. So what I want to show you here is what's happening. So again, calcium chloride, that salt is going into water and it ionizes. We make calcium ions and we make chloride ions. The reaction that's taking place is the solid CaCl2 is ionizing into these products right here. We want to know what is the enthalpy of the reaction. Now, remember that there is the law of conservation of energy. So when this reaction is taking place, there's a certain amount of heat that is being exchanged. We see a temperature change, so there's definitely an exchange of heat. And we see that the temperature that is measured, it goes from 20 degrees Celsius to 37 degrees Celsius. Think for a moment, what is that? How's that going to feel in your hands? It's going to feel warm. It's going to feel warm. I'll switch to red. So this is going to be an exothermic reaction. The temperature went up. The temperature went up, so that means that it's exothermic. Okay? That's something to keep in mind really, really fast. Temperature goes up, it's exothermic. Now, we still want to figure this out. We want to know at the end of the day the enthalpy of the reaction. The enthalpy of the reaction can be broken down into this. It can be broken down into an equation. It can be Q over the number of moles of reactant, which Q is MC delta T over the number of moles of reactant. So that's kind of the big deal equation with finding this value right here. Then MC delta T comes back. Now, how can we find MC delta T? That's not too bad because remember the law of conservation of energy. So I'm going to say this. I'm going to say that the Q of the reaction, this process right here, the amount of heat in the reaction that is happening is going to be equal to the amount of heat that the water is gaining. Now, it's an exothermic process. The temperature is going up for the water. So I'm going to put plus sign for the water. It's gaining the heat. and it's an exothermic process for the, let me say that one more time. I think I messed up. The reaction is losing heat because the water is gaining heat. Its temperature is rising. So negative Q for the reaction, the heat is going into the water because the temperature is going up. So I'm going to put a positive value for that. So wherever heat is going, that's the temperature increase. Wherever heat is leaving, the temperature for this reaction is going down. So negative value exothermic process for the reaction, positive for the water. The water is increasing in temperature. This is a lot of weird stuff going on here, so stop the video if you need to. Talk to me, send me messages if you're confused. But there's all these negatives and positives here have a meaning, and it's important to keep them straight. And I know it's weird, I get it. But I'll say it one more time. For the reaction, this reaction taking place, it's exothermic. How do I know? Because the temperature is going up for the water. So it means the reaction must be exothermic. And because I know this, there's a law of conservation of energy, I can correctly calculate the amount of energy in the reaction. And it's equal to the amount of energy that the water gained. So the Q for the water is going to be mc delta T. We have 50 milliliters of water. So we have 1 gram per milliliter for density. We have 50 grams of water. The specific heat, so 4.18, and times the change in the temperature of the water. The change in the temperature of water was 20 to 37. Its final temperature was 37. Its initial temperature was 20. Okay, so the amount of heat that the water gained is going to be 50 times 4.18 times 37 minus 20 is 17. So 3553. 3553, and that's just in joules. Okay. So the Q of the water is equal to 3,553 kilojoules. Now, that is an equivalent amount of energy to the reaction. It's just flipped sign. So the Q of the reaction is going to be negative 3,553 joules. We want to go back to figuring out reaction, the enthalpy of the reaction. So I've got the Q part done. But I also want to keep in mind that enthalpies are in kilojoules. So I'm going to switch this over to kilojoules. So there are 1,000 joules in 1 kilojoule. So it's going to be negative 3.553 kilojoules. Right? So that's how many kilojoules of energy were released in this process. And so delta H is going to be equal to negative 3.553 kilojoules over, and then that's going to be underneath there the number of moles of reactant. Well, how many moles of calcium chloride dissolved in the water? 5 grams did, so let's convert that to moles. 5 grams CaCl2 down here. I don't know the molar mass of CaCl2 in front of me. I don't have a periodic table right in front of me either. Oh, I'm terrible. I'll just look it up real quick here. About 111. About 111. So 111 grams CaCl2. So 5 divided by 111.045. All right. So delta H is equal to 0.045, or excuse me, delta H is equal to negative 3.553 kilojoules per 0.045 moles of CaCl2. Just do the division. So 3.553 divided by 0.045, and we get 78.95. Let's just go with 79. Let's just go with 79. Let's just use two sig figs. So 79 kilojoules per mole. But that negative is important to keep in there. So negative. So we just found the enthalpy of a reaction by figuring out how much heat is released when this occurs. We did that by looking at the temperature change, 20 to 37 degrees Celsius. We remember that there's a law of conservation of energy. Energy is conserved. Energy is not just willy-nilly given off. It is conserved. When this reaction occurs, the amount of heat that is released out of the calcium chloride is received by the water. That's why I could write this. The reaction is losing the heat. The water is gaining the heat for the reaction. This is an exothermic process that feels warm in your hands. The temperature goes up, and then we can find the amount of heat that the water gained. We can't find the reaction. Why can't I find the reaction directly? Because I don't know the specific heat of salt, this CaCl2. I don't know the specific heat of those ions. But it doesn't matter because I know the specific heat of water. I know the water's heat. It gained that heat from the reaction. So I can figure out the magnitude, but not the sign from this calculation here. And then I just plug in my values here. So 3.553 kilojoules divided by the number of moles of calcium chloride, and then we get the enthalpy of the reaction, negative 79 kilojoules per mole. This is a big deal kind of problem right here. There's a lot going on here. I'll do a few more examples, but this video is probably already super duper long, and I want to give you some chances to actually work out these kinds of problems. I'll put them on Schoology over the next couple days. But this is kind of like the big deal problem I want to get us to do ultimately. Couple things just as announcements. I had a crap ton of you guys asking me to extend deadlines and stuff like that. I am flexible, but there is got to be a point where I can't keep extending deadlines. Like grades were due today. And I can't keep opening deadlines for people who don't do the assignments. You need to get the assignments done in a timely fashion. I know the first week that we had quarantine, like some storms happened and people's Wi-Fi was down and stuff like that. I get that. But, I extended the deadline for another week, and I still had people Monday night trying to get me to open the deadline. I'm not going to do that, guys. That's not cool. That's not fair to people who did it earlier. You need to be able to manage your time and get things done in an appropriate amount of time. You can come in. My wife's over there. So please get things done. If something horrible happens, let me know. But if like my kiddo's in here. But if I can't just keep doing things like keep extending deadlines. That's not fair. That's not good for you. The world does not keep extending deadlines when you fail to manage your time properly. You need to be able to manage your time properly. So homework is due for this week on Friday, and I'm not extending the deadline anymore. You've got to manage your time. We're going to be online the whole rest of April. You're going to have to figure out how to set up time for you to finish work and listen to these lectures and learn the material. I'm posting lots of things from like Khan Academy and various other YouTubers who do chemistry as well. Watch those, learn from that, do the math, do the problems. If you're not learning the material, then you can ask me for help, but we are in a weird situation where I'm not available after school or before school to go through problems with you. So this is the best we can do really right now, and I can lead you to YouTube videos and stuff like that, but there's not a whole lot more I can do than just sort of maybe do problems in front of you on a recording and stuff like that. But, we're doing the best we can. I'm available for help no matter what. Happy to help all the time. But at the same time, you've got to have some discipline. You've got to build up some grit in this situation and learn this material to an extent on your own. And that's kind of life a lot of ways too. I hope you guys have a good rest of the week. I will be posting one more video later on going over another kind of problem that we did for homework. I think the homework for today on Wednesday is some more MC delta T kind of problems. This stuff is for Thursday, and then on Thursday I'd like to put up the answers essentially to Wednesday's problems. So hopefully this is making a lot of sense. If not, send me a message. Please use that discussion board too. I put up the discussion board for people to kind of post questions, and then a lot of people may have the same questions so they can read that. All right, have a great day. See you guys.